Friends, welcome to the tutorial series on network analysis made simple. During the previous tutorials, we have studied Thevenin's theorem, Norton's theorem, maximum power transfer theorems and so on. Also, I hope you have gone through my earlier tutorials on Kirchhoff's laws, mesh current method, node voltage method and so on. These previous tutorials I feel are the basis for network solving. Friends, any theorem that we study, finally we arrive at applying one or the other network solving method to find the unknown. Therefore, I suggest you go through those tutorials and get confidence and skill to choose suitable network solving method depending on the circuit you get after you make some modifications such as making sources 0, opening the load branch and so on. Friends, during this tutorial we shall study superposition theorem. Friends, first let us understand what is superposition in general and superposition theorem in particular. Superposition principle is a simple concept known centuries ago. It has numerous applications in various fields of science and engineering. In general, superposition principle states that the solution to a linear system involving multiple inputs is equal to the algebraic sum of the individual solutions considering each input at a time. Before we go to the study of superposition applied to electrical networks, let us see some interesting applications in other fields also. For example, in civil engineering, a beam can be modeled as a linear system where the input stimuli are the loads on it and the output response is deflection. Since the system is linear, superposition principle can be applied. In mechanical engineering, the superposition principle is applied in the study of vibrations. We know that a vibration is an oscillatory motion. Oscillations can be produced due to either internal or external forces. As long as the oscillations are linear, superposition principle can be applied. Friends, in the well-known Maxwell's equations, the distribution of charges and currents are related to electric and magnetic fields by linear transformation. Thus, the superposition principle can also be applied there also. Friends, very important application are in wave superposition. In many cases, the equations describing sources and responses will be the waveforms either sinusoidal or non-sinusoidal at a given time. These waveforms are described by wave functions and the equations governing their behavior are called as Schrödinger wave equations named after the great scientist Erwin Schrödinger. The responses caused by two or more waves traversing the same space is the sum of the responses that would have been produced by individual waves separately. Friends, another major and very important application is in quantum superposition. Superposition is a principle in quantum theory that describes a challenging concept about the nature and the behavior of matter and forces at the subatomic level. You know that this study has led to the development of the most modern nanotechnology. Friends, quantum superposition is a fundamental principle of quantum mechanics. It states that any two or more quantum states can be added together and the result will be another valid quantum state. Mathematically, it refers to the property of solution of Schrödinger wave equation. Since the Schrödinger wave equations are linear, the superposition can be applied. Erwin Schrödinger, a Nobel Prize winning Austrian physicist, is considered to be one of the most brilliant scientists of the last century. Friends, I wish to dedicate this tutorial to this great father of quantum mechanics, Dr. Erwin Schrödinger. Friends, These are only few examples I stated to create interest in the study of superposition theorem applied to electrical networks. Let's go ahead. Friends, we know that the network theorems in general are the procedures described to solve the networks. Solving any network, we mean finding current through the branch or voltage across the branch or across any circuit element. Remember, superposition theorem is applied to a linear networks having multiple sources present in them. The meaning is simple. We know that when the number of sources are present in a network, the response in any branch is the combined effect of all the sources present. Therefore, superposition theorem states that in any linear network containing more than one independent sources, the response in any branch of a network is the algebraic sum of the responses obtained by considering each source acting separately, during which time the other sources are made 0. Why algebraic sum? Look, when we find the response considering one source at a time, if the response is voltage, we have to keep track of its polarity while finding the resultant response. If the response is current, we have to keep track of its direction. Friends, then let me summarize the procedure to apply superposition theorem to a network. The first and the foremost is observe the network carefully, consider one independent source at a time. Next, redraw the network making the other sources 0. You know that voltage sources are to be short circuited and the current sources are to be open circuited to make them 0. Friends, after the sources are made 0, observe the changes in the connectivity of the network elements carefully and then apply suitable circuit solving technique and find the response required. Repeat the procedure for all other independent sources, taking one at a time. Finally, take the algebraic sum of the responses to find the total response. Friends, I hope you know the Fourier series. In this, a non-sinusoidal waveform can be represented by an infinite sinusoidal waveforms of different amplitude and frequency. You can see here in figure that a non-sinusoidal waveform and a fundamental, second harmonic and the third harmonic waveforms are shown. So, we know that V of t is equal to V1 of t plus V2 of t plus V3 of t plus so on. Now, you can visualize this equation and see that it is nothing but a superposition theorem, isn't it? Friends, having understood the basics of superposition theorem, we now are ready to solve few numerical examples. Let's go ahead. Friends, consider the network shown in figure. We are required to find the current in 6 ohm resistance using superposition theorem. Observe the network carefully. There are two independent sources, one of the voltage source of 18 volts and the other of a current source of 3 amperes. To apply superposition theorem, we have to consider one source at a time. So, first let us consider the voltage source of 18 volts. The other source has to be made 0. We know that to make the current source 0, we have to open circuit it as shown in figure 2. Let I1 be the current in 6 ohm resistance due to the voltage source only. By observing the network, we find that it has turned out to be a single loop network in which I1 is flowing in the clockwise direction. By writing the Kirchhoff's voltage equation for the loop, we get 6I1 minus 2Vx minus Vx minus 18 is equal to 0. But Vx is equal to minus 1 into I1. Let me clarify why it is minus 1 into I1. See that the current flowing through 1 ohm resistance is from left to right, but the polarity of Vx given is plus on the right side and minus on the left hand side. But we know that current in the passive element will flow from a higher potential point to a lower potential point. So, the drop in 1 ohm resistance should have the polarity opposite to that of the given polarity of Vx. Therefore, Vx is equal to minus 1 into I1. By solving this simple equation, we get I1 is equal to 2 amperes. Note the answer is positive, which means current will flow in the clockwise direction. Next, consider only the current source of 3 amperes. The voltage source of 18 volts is short circuited as shown in figure 3. Let I2 be the current in 6 ohm resistance. By observing the network, we find that it has turned out to be a 2-node network. To find I2, I prefer to apply node voltage method. Let V1 be the node voltage as shown. By writing the nodal equation for node 1, we get V1 divided by 1 minus 3 plus V1 plus 2 Vx divided by 6 is equal to 0. But V1 is equal to Vx. By substituting and solving, we get I2 is equal to 1 ampere. Again, note the answer is positive. Therefore, the total current in 6 ohm resistance I is equal to I1 plus I2, which will give us 3 amperes. Friends, next consider another example to find Ix in the network shown in figure. The strategy will be same as that we followed earlier. Consider only the voltage source of 10 volts. The current source is made 0 by open circuiting it as shown in figure. Note now, no current will flow through 3 ohm resistance. Let Ix1 be the current in 2 ohm. So, we get Ix1 is equal to 10 divided by 3 amperes. That is simple. Next, consider only the current source and short circuiting the voltage source. The network drawn is shown in figure. It is interesting to note that 1 ohm and 2 ohm are in parallel and 2 ampere enters this parallel combination. So, by using the current division theorem, Ix2 is equal to 1 divided by 3 into 2, which will give us 2 by 3 amperes. Therefore, the total current in 3 ohm resistance is Ix is equal to Ix1 plus Ix2. By substituting, we get Ix is equal to 4 amperes. Friends, now let us solve a very simple but tricky problem to find Vx using superposition theorem. Observe the network carefully. There are two independent sources, one of 4 volts and the other of 2 amperes. Also observe that there is one voltage controlled voltage source of 3 Vx volts, which is dependent on Vx, which is the voltage across A and B. First, let us consider the voltage source of 4 volts. The current source is made 0 by open circuiting it as shown in figure 2. Let Vx1 be the voltage across A and B. Note, 1 VAB is open, hence no current will flow through 10 ohm resistance. Second, the voltage controlled voltage source now is dependent on Vx1, which is the voltage between A and B. So, by writing the Kirchhoff's voltage equation for the circuit, we get Vx1 plus 3Vx1 minus 4 is equal to 0. By solving, we get Vx1 is equal to 1 volt. That is simple. Similarly, now let us consider only the current source of 2 amperes. By short circuiting the voltage source, the network is shown in figure 3. Let Vx2 be the voltage between A and B. Observe the network carefully. Note that the dependent voltage source is now dependent on Vx2. Number 2, the current of 2 amperes will flow from right to left in 10 ohm resistance. Number 3, Vx2 is the voltage across the current source of 2 amperes. These are the important observations you have to make. Therefore, in view of the above observations, by writing the Kirchhoff's voltage equation for the circuit, we get Vx2 plus 3Vx2 minus 10 into 2 is equal to 0. By solving, we get Vx2 is equal to 5 volts. Therefore, the total voltage Vx due to both the sources is Vx is equal to Vx1 plus Vx2. By substituting, we get Vx is equal to 6 volts. Is it not interesting, friends? Next, let us consider another problem to find Ix in the network shown in figure. By observing the network, we find that there are two AC voltage sources present. By considering only a voltage source of 20 angle 0, let us short circuit the other voltage source to make it 0 as shown. Let V1 be the node voltage and I1 be the current through 10 ohm resistance. By writing the nodal equation, we get V1 minus 20 angle 0 divided by J15 plus V1 divided by 10 plus V1 divided by minus J5 is equal to 0. By solving it, we get V1 is equal to 7.95 angle minus 143 volts. Therefore, current I1 is equal to V1 divided by 10. By substituting, we get I1 is equal to 0.795 angle minus 143 amperes. Similarly, next consider another voltage source of 10 angle 90 volts. The other source of 20 angle 0 volts is short circuited as shown. Let V1 be again the node voltage and I2 be the current through 10 ohm resistance as shown now. By writing the Kirchhoff's nodal equation, we get V1 minus 10 angle 90 divided by minus J5 plus V1 by 10 plus V1 divided by J15 is equal to 0. By solving, we get V1 is equal to 11.96 angle 126 degrees and I2 is equal to V1 divided by 10, and by substituting it, we get I2 is equal to 1.196 angle 126 amperes. Hence, current Ix due to both the sources, we get Ix equal to I1 plus I2, and by substituting the values, we get Ix is equal to 1.4245 angle 159.9 amperes. Friends, in this tutorial, the basic concepts of superposition and superposition theorem is explained clearly. Few examples are solved to emphasize the concepts learnt. Also, relevant skills of identifying the network connectivity after making the sources 0 are also brought out by taking suitable simple numerical examples. If the tutorial has ignited some of your thoughts, please forward your feedback and suggestions to my email. Thank you for watching this video.